Hello everybody and welcome back. Right now we are talking about Organic Chemistry, Chapter 12, Separations and Purification Techniques. So we have a bunch of chromatography, types of chromatography to get through, so let's get started. We have our gas chromatography, okay, which separates based on boiling points and volatility, which means volatility means the tendencies of that substance to turn into a gas, okay? And in this case, the gas is going to be your mobile phase. So you're just going to have a different boiling point, which means the compounds in the mixture are going to elute at different times. Okay, so, and when I say elute through the whole portion of this video, that just means come out, basically. So next we have our affinity chromatography, which uses, which separates based on the lock and key interactions, okay? So we have an example here. We have our mixture, okay? And in this case, we're using an antibody. It does not have to be. This is just a good example. So we have our mixture with purple and white dots, right? So now we are adding our antibody, which is going to bind to one of the specific proteins in that mixture, which it's going to be the purple one. So now you can see they have, those antibodies are attached to that specific protein, okay? Which means when you flush out the rest, those antibodies cause that protein to have a high affinity for the column, which means they are going to stick to the column even when you put something through the column to flush out the rest. So that's how you're going to separate that mixture based on affinity. It's when one of the substances has a high affinity for the column. All right, next we have our ion exchange chromatography, which separates based on charge. So in a cation exchange, you are going to retain the positively charged molecules, okay, that you had in your original sample. And then in your anion exchange, you're going to retain the negatively charged molecules, okay? So here we have a mixture. Okay, there's a negative, positive, negative, positive, negative, positive, right? Then you're going to add a solution which has like a higher attraction for example here, right? We have SO3 Na+, okay? We're going to add another more strong positive charge to attach to SO3 instead of Na+. So when we add our strong positive charge, SO3 is going to attach to the more strong positive charge that we just added, and it's going to let go of that Na+. Okay, and then the Na+ is going to be able to come out in solution, or elute in our from our column. So that is how we use this method. Okay, so you can see now they're separate. We had the SO3 and the Na+ together. Now we have SO3 with something that we added, as well as our Na+ with a negative charge that we added. So that's how you separate those two, and then you just have to take it one step further, and then separate the what we've just added into our column, if that makes sense. Next we have, stand it on this side. Next we have our high performance. Next we have our high performance layered chromatography. So this separates based on polarity, okay? So our mobile phase, so the phase that is moving, is going to be non-polar in this case, okay? And most of them are, except for reverse phase HPLC, okay? And there's another one as well that I think we get into in another video, but for the most part, your mobile phase is going to be non-polar. That means that the non-polar part of the mixture is the one that's going to be moving or eluting and things like that. So we put on a sheet like this. You have your mixture here, and then you put your mobile phase through this tray, which means that the non-polar substance in your mixture will elute first, right? Because if you have your mixture here, and we're putting in a mobile phase, so the thing that's going to move it through, and it's going to be non-polar, that means that like dissolves like. So the non-polar mobile phase is going to like the non-polar compounds in this mixture, so it's going to carry it with it as it goes through the tray, which means our non-polar part of our mixture is going to elute first, and our polar mixture is going to not elute as far, right? It's not going to be carried as far with our mobile phase because it's polar, and the mobile phase is nonpolar. So that is how you would separate based on polarity. Next, we also have reverse phase HPLC, which is the same technique, but mobile phase would be polar. Okay, so it would just technically be the opposite of this example. But it would have to say reverse phase. Okay, like I said, for the most part, the mobile phase is going to be nonpolar. Next, we have our column chromatography, which separates based on polarity. So here, so we have the next couple also separate by polarity, but the column chromatography is able to do so by much larger amounts. Okay, so this is good for large amounts. So you have your silica gel, which is polar, in your column, and then you're going to add your mixture. Okay, and then what's going to happen is, like we saw earlier, the non-polar parts of your mixture are going to be attracted to the polar silica gel, and then the non-polar parts of your mixture are going to try to get as far away as possible from the silica gel, and they will also group together, okay, which will cause the non-polar substances to elute from your column first. And again, that's how you separate by polarity. Non-polar and polar in your column will separate when you add the silica gel, okay? Next, we have thin layer chromatography. If I said high performance layer chromatography, I meant to say high performance liquid chromatography. Okay, just a note there. So this one is high performance liquid chromatography, HPLC, and this one is TLC, which is thin layer chromatography, just to clear that up in case I misspoke earlier. So our thin layer chromatography separates based on polarity as well, and it uses the silica gel, which is polar, which is our stationary phase, okay? So what you'll see here is a card, okay? And you're gonna have your mixture down here. And what happens is you add your, you have this on a polar stationary phase, right? So what happens is the polar molecules in your mixture will stay at that stationary phase, right? But what happens is the non-polar substances will move further away, which means that the nonpolar substances would be up here with the solvent front. Okay, so basically you can separate based on polarity by looking at the distance migrated. So I'll say it again. If you have your mixture here, right, because your stationary phase is polar, that means that the polar molecules inside of your mixture are going to stay with their stationary phase, right? They're not going to move. They're going to stay with the stationary phase. But your non-polar molecules, because they do not like polar things, they will try to move away from the polar phase. And that's why the solvent front is going to contain mostly your non-polar molecules, okay? And this is also where we start to talk about RF values, okay? So RF is basically we're looking at the distances. So you're going to do the migration distance, okay, over the solvent front distance, for example. So we have our polar here would be B, and we have our non-polar part, which is, molecules, which would be A. So if we were trying to find the RF values for A or B, you would take the migration of A or B, okay, and then divide it by the solvent front distance, which would be up here. So you would see that the non-polar ones would actually have a high RF value, okay, because these two things are closer together, the solvent front and the non-polar migration, compared to the polar substances, which would have a low RF value because they did not move as far as the solvent front or the non-polar molecules, okay? So definitely look at an example of that, but that's just in short an easy way to look at it. Finally, we have our size exclusion chromatography. Sorry, my example's on this side. Our size exclusion chromatography down here. So it separates based on size, and so the small molecules will elute last. So what happens in this column right here is you would have a kind of like a pathway, if you think of it. And the big molecules would not be able to fit through the tiny tube that you put all through the column, right? So the big molecules would just have to fall right through the sides of the column, whereas the smaller molecules would be able to fit in these tiny little pores that you put, and they would take a long time to travel all the way through the column, which is why the smaller molecules would elute last and the bigger molecules would elute first. Okay? Now, if we're looking at distillation, which is just another form of separation purification that we did not write on the board, but there's one, I just wrote it there at the bottom. There's just one difference between the two types of distillation. So there's simple distillation, which you would use when you have a difference greater than 30 degrees between your two substances that you're trying to separate, okay? And then fractional, okay, you can think of it smaller, fractional distillation would be used when you need to be more specific, when the difference in boiling points for the two things that you're trying to separate is less than 30 degrees, okay? So that's just two ways to separate as well. But yes, if you have any questions, please put them below. And we'll see you in our next video.